This is based on something I did for a company in Quebec in November 2022. They contacted me because they were moving from C++17 to C++20, and they wanted to know what the fuss was about. Like, why should we do something like that? Would we have fun? Well, I said, what do you do? Well, they said, we have this product. You know, so it exists, it works. It does I/O, it does parallel and concurrent processing of data, as you can see. We have managers, singletons and stuff. We'd like to get rid of them, but it's not always easy. We do some compile time stuff to choose algorithms, kind of like what you do in the standard library sometimes. And it works. You know, we have something that makes money. So it's cool, we're not gonna change it. But we accumulated technical depth over time, and we're wondering, well, maybe now is the time to rethink our processes and see if we're doing things right. And if changing language versions is just a matter of being cooler, or if it actually brings something to the table. So we'd like to know about that. So we don't know. So I asked them a few questions about what they were doing, and I tried to build a reduced version, very reduced version of what they're doing. So it's a toy thing, okay? But it does essentially what they do at a much simpler level. So yeah, so that was the question. What could we bring, what could we get from that move we're trying to make from C++17 to C++20? Let's hope it gives us something interesting to talk about. So you have to be warned, of course. It's an artificial thing we're going to be looking at that does the things that an actual real project that makes money does. This one doesn't make money at all, okay? And there's no way we can cram C++20 into an hour talk. It's not going to work. It's huge, it's gigantic. When I built my actual C++20 slides for courses I give to the game programmers, which is what I usually do, I couldn't make it fit in 2 days. I mean, it's a 3-day course if they take the whole thing. So most of the time they handpick stuff to make it fit in 2 days, and then they say we'll read the rest because they can't free themselves for 3 days in a row. So we'll barely touch it really, but enough to get a taste. And you probably had a taste already, most of you, from what I can understand. In some cases, the features I'm going to be using are going to slow me down a bit because they're not the right tools for the job I used. But that's interesting too. I knew that though, to be honest. But it's fun to put that forward, that it's not magic. And yeah, well, overall, let's see if it does bring results though, because if you're making a move like that, you don't want to slow down your code. You don't want to make it harder to maintain or manage. Yeah, so this is a slight slide on me, if you don't know who I am. I've been doing this for a while, not as long as Kate. Whoops. This is an evil wire. It's gonna come back, I guess. So let's see if I unplug this and replug it. We have fragile wires this morning. Did it come back? Otherwise, my expert friends will help me around. Thank you so much. So, I've been doing this for almost 40 years, really, to be honest, but more than 30, that's for sure. I have 5 kids, which means that when I'm giving classes from home, there's noise. I have a host of animals. You just saw on screen one of them, but there's a number of them. Let's put it this way. I was asked recently by one of my bosses, how many do I have? Yeah, this is the one. Yeah. How many do I have? And I said, I don't know. I can figure it out. I'm gonna get there. Thank you so much. This is where I was. That's it. We actually have a shelter. So my wife is somewhere in the building today because she's working remotely, but we have an animal shelter, which explains that all of our animals are damaged and stuff like that. I've been teaching since 1998, so this is my 25th year. It's something that I like to do, to be honest. I do that both in college and university. I work a lot with game programmers. But this is not my only clientele. I actually work with students in general, but I do give a lot of classes to the games people. And that explains my involvement, among other things, in the WG21. I've been there for 10 years now, and in SG14, which is our study group for low latency stuff. So I do give perf talks. This one is not really one of them, but still. I will be giving another talk tomorrow that was not planned. I learned about that yesterday afternoon. So it's going to be a live coding thing where we'll be killing orcs. So if you want to kill orcs with me, come tomorrow. You'll see we can get speed from that. It's going to be fun. Okay, so where are we starting with? When you get the slides, because they will be published, they probably already are, you get all the source code. So if you want to complain, go and have fun, okay? But this is artificial, and we have to know about that. So we're starting from what? We have a system like theirs. The company is called Innovmetric, very nice people, very proficient. So they have a system that performs analysis on mechanical pieces. So pieces come, they look at them with cameras and stuff, and they take metrics and they reject the stuff that's defective, log, do some reports on what they got. As you will see from the names I used, I'm not a domain specialist. My wife builds the furniture at home. I don't. She's very good though. There's something that feeds pieces to our product, and then we diagnose the pieces afterwards. I will be doing randomness-based generation of data, so data will vary from time to time, but generally speaking, we're talking about a gigabyte of data. Then there's a summary analysis that's been done on the defective pieces to know why we rejected them, all random in my case. We'll see the code. And then we'll do a more in-depth analysis on what we kept, the non-defective ones. This one will, like in their code, involve some concurrent programming. So I have a small thread pool that I wrote for the sake of the example. And all of these pieces were written in C++17 and then adjusted for C++20 a bit to see if there's a reward to that. There. At the end, I produce a report, which is a very big file that I take care to delete after a while because it takes space on my disk. So the overall program looks like that. Cool. This is the general idea. Kate was saying this morning, I take notes when I write. Sometimes when I don't know what I'm going to be doing, I write comments before I write code myself. The comments tend to go away after a while because the names I try to use, I hope they're good, you know, but the comments guide me at first. So creating pieces, then processing them sequentially to make the first diagnostic stuff, then looking at why I rejected stuff, producing some stats, computing some quality values there, and doing the more in-depth analysis. All of this is artificial, of course. So I did pieces, of course. I didn't know what name to use there because I'm not an expert, so I did mechanical pieces. Then I have an idea, and they have values in there, strings, integers, floats. The float is a quality level there. It tells me if the piece is good or not, randomly generated, and I have some threshold at which I say, well, they're not good, I reject them. It's, as I said, artificial. And the way I evaluate quality, as you can see there, is that I make a sum. Well, instead of really a sum, I take the max. Accumulate is cool. Algorithms, Connor's in the room, algorithms are awesome, and some people will complain about the name accumulate, but I like it. So I keep the maximum quality that I found along the way, and I decided that this is the overall quality of my piece. It's totally arbitrary. I could do something else. This is what I took. This is what I based my computations on. I decided that since I had elements in there, I could iterate through them. So I took something that looks like a container interface with begin and end. This is a kind of code that looks so much better in C++23. But I don't have C++23. When I write this, it's a C++20 thing. But if you haven't looked at deducing this, for which one of the authors is in the room right now, you're going to love C++23 so much. It's one of the things I'm looking forward the most when I do these things. So this is basic stuff. A few constructors, as you can see, nothing major, initializing my data members. I have a vector of elements that could be empty in some cases, an ID, whatever. And I can compare pieces. So relational operators that we write, there's 6 in this case. You know there can be a number of these when you have mixed types too, but I decided to restrain myself to comparing pieces to pieces. Now the equal, and different from are not very difficult to write, as you know, but it's kind of boilerplate-ish because the only reasonable way to write different from is to reuse equal. And then when you start writing something like less than and it's complicated, you don't want to write the other ones by hand. You want to reinvest less than in the computation of the others, otherwise it's a mess. So yeah, a lot of code there for something that could be trivial, but hey, why not? And a number of other stuff that we'll leave aside for a moment to input and output elements and know what the quality of something is, minor stuff, so pieces. Let's start with that. Then I have to create the pieces for the sake of my computation. Now I'm generating them randomly. A better use case would be to read them from a file, just didn't get around to it. I should pre-generate them and then consume them. My test would be more stable, but the scope of this thing doesn't change much, to be honest. So I went with 10,000 pieces. I love those decimal markers on numbers. I've, if you'll allow me for a few seconds, on my C++ 14 slides, I have a slide somewhere that says, we used to write it like this, now we write it like this with the markers. There's an actual mistake on the slide. It's missing a 0 on the one that has no marker, and nobody ever notices until I tell them. So it's awesome. And up to 7 elements per piece. So it's an upper mark. And the code kind of looks like this if you look at it. So I'm going to create pieces and measure the time it takes. So that's why you have that testing that's not highlighted, but will be in another slide. I'm going to test the time it takes for me to do things, because speed does have an importance to me. So, and then I'm going to format the integrals I display on screen, because I like them to show up with those little markers too, because they read so much better. But that's not the way integrals are displayed when you display them, is it? So if you display 10,000, it's going to look like one with a bunch of zeros, and you're going to have to count them. And that's not good. So that format integral thing, it's all trivial code, to be honest. Something you could all write. There's nothing magic. So I have this small pad left thing where I'm padding with some character up to a certain width, a string, to the left, because I'm adding zeros in most cases. I have this absolute value thing that doesn't care about unsigned integrals. Just let them pass through. And I didn't use IBS there because IBS was not constexpr, even with C++20. So I wrote a homemade absolute value thing. It's tricky, because absolute value, when you get to something like the minimum value for a short, doesn't give you the right result. It's undefined behavior, and you cannot do that in constexpr world. But let's suppose it doesn't happen. I heard you laugh. And that format integral thing there, well, I'm taking care that I have an integral type t, so I have a static assert there. That's fine. The code won't compile if I pass a float there, because it's not meant for floats. But it's within my code, it's not in my interface. And I find out whether or not I need a sign, and I compute the absolute value, and then I have this gymnastic that chops the thing into 3-digit blocks to display it nicely. Not particularly fast, but it works, And if you look at the code, it's going to give you something like that. So it's fine. It's not something that I use for speed anyway. It's reasonably fast. Okay, cool. So I'm guessing that reads better with the ticks there. So what's that test thing? Because I use that a lot in my code. Here in other classes, I like to be able to measure stuff efficiently when I do code. Some people might complain, I can do better. Fine, but this works nicely. So if you look at the way I wrote this, I'm returning a pair that has a value, the value of the computation, so I don't take any void functions there, and the time it took, which I then duration cast whatever I want to use as a resolution. So it looks kind of like this. If you don't like the ... things, don't worry about it, it just works. Okay? But the thing is, it calls f with argument args, relaying them properly, takes the time before, time after, and returns a pair of what I computed and how much time it took according to that clock. And that's it. It's important to have a result, because your compilers are crafty. If you don't have any side effects, you'll probably end up with no code at all. It's going to be very fast. There. So I'm creating pieces and trying to measure the time it takes. Fine. So creating pieces, what does it involve for me? Well, I need names. And I really am not a mechanical person. Okay? So I found names that I thought looked like mechanical pieces names. So not bolt, power supply. No clue if it's relevant. Okay? But that's okay. People laughed at me. That's fine. And I have this dice that I'm going to roll to pick a name at random, which means that my code is not thread safe. Cool, but that's okay. It's not meant for multi-threaded code, but it still deserves some kind of comment. I think I have one in the slide somewhere that's not thread safe and not marked as such. You have to be careful. You all see why it's not thread safe, I hope? Okay, because I have state that I'm sharing. So there, and I'm combining names with operator plus. Now, if you're wondering, C++17, you have string view. Why are you passing const string ref? It's because I'm using operator plus with strings. It won't compile otherwise, which makes me sad. because why not? If you add a string to string view, why not get a string out of it? But that's not what we have as an API right now. And then when I'm creating the pieces, while I'm making a vector, I know how many I need, so I'm just resize everything right away because I don't need to resize many times. I'm okay. And then again, this is not thread safe. Well, no, this one is thread safe. It's okay. So I'm making a random number generator, and I'm creating pieces in a loop. So there's one big allocation and a number of additions to the vector. It's reasonably fast, given the task I'm asking. What's longest to do in there is rolling the dice. It takes forever, to be honest. Cool so far? Cool. And there, when I'm creating one piece, because creating pieces means creating a piece many times. Otherwise, your function is too long, isn't it? Okay. And then I have another vector there because I need elements. I have up to 7 elements. So I'm creating something, rolling the dice, and creating the elements in there. So 2 vectors involved, allocations and stuff. Works. So I'm creating my stuff. Questions about this? So we're creating pieces so far. Cool. Then we need to sequentially process them. So one at a time, and good, bad, 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 good. I'm going to throw away very few of them, but still. So I made the singleton because they told me, well, we have a singleton for that. So let's look at what it gives. I'm taking one call to my getter that might instantiate the singleton. The reason I'm doing that, as you'll see later, is that it's the Myers singleton that people call it. So something with a static variable inside the function, which means it's created on the first call, but which also means it's guarded by some synchronization mechanism that you're going to pay on every call. So if I'm going to be using the singleton many times in the same function, I'm going to call it once and keep a reference to it to avoid paying the cost all the time. I'm taking each of the pieces and I'm diagnosing them. If it's good, say, good, it's valid, it goes in the valid bucket. If it's not, well, it's defective, I'm rejecting it for some reason, the reason that I found. Cool? I love the new ifs that we've had since C++17, those where you have an initialization followed by a test. I really like them. I like the variables that live for a short period of time. I love them. It's preferable to make smaller functions, but sometimes it's just the thing that you need. Now, this is going to be tested, of course. So I'm going to test the time it takes because it's sequential processing of a number of pieces. It's fun to know if it takes time or not. I'm going to want to compare that between my 2 versions, of course. So the diagnosis thing, I'm going to represent my diagnosis by a type, but it's very simple. The piece is okay or not. If it's not okay, there's a reason. As you can see, in the case where okay could be false, well, there's a reason. I'm making sure that it's not okay because there's no reason to keep it. There are reasons to reject it in the scheme that I put forward at least. Cool? Diagnosis. And then when diagnosing, well, I don't know how frequent rejects are in real life. I guess it changes from company to company, from domain to domain. So I went scientifically like this. See? I decided on 2% or something like that, which is probably a bad day at work, which is what I work. I'm guessing they're better than that. So I'm rolling the dice about 3. I'm checking the quality is high enough, and if it's a reject, I'm rejecting it. And if it's a reject, indeed, I find the reason for that rejection, which I don't know beforehand. So I have to find a way to determine a reason, which is, again, totally not thread safe. I'm picking a reason at random from a set of 3 that I could imagine. It's totally artificial, but it doesn't change anything to the structure of the thing. Cool? If you're saying, I know my mechanics, this is bad, I believe you. Cool for that? There we go. Good. So then what I do is I take my piece that I'm rejecting and my reason, and I'm moving them to some kind of map or something like that. It's going to keep them together. My analyst there, what does it look like? Well, it has a map of rejects, a vector of rejects, and a map of reasons. I'm going to compute for each reason that I know of the number of occurrences. So how many of them did not pass conformance tests, and how many of them were just malformed or things like that. It's a singleton, so it's not computable. It's a Mayer singleton, as you can see from the middle there, that get thing, that returns a reference to the singleton that lives inside there. There's a cost to that, as I said, so you have to be aware that you did it that way when you're calling it. And the rest, there's a way to get stats out of it and something like that. Pretty simple stuff. Cool? Cool. Now that reject thing there, when I'm rejecting something, I'm just computing that, well, the piece has been rejected, and the reason for rejection, well, there's one new occurrence of that. So I'm just taking notes. At some point, I'm going to need stats. What happened, you know? Well, my stats, I'm just accumulating. I could do an accumulate there. Accumulating the reasons and number of occurrences of each into a big string, and I'm getting that out afterwards. I use a string stream there. If some people in the room tell me that thing is slow, the constructor is slow. But I'm constructing it once and using it quite a bit after that. It's a good tool. As someone said this morning, someone very famous, sometimes you don't need to be all that fast. I mean, the construction there, I'm not calling that often, I'm calling that once. Who cares? Cool. So far, so good. Then get to the point where we need to do some computation, like what's the average quality of the good pieces, the bad pieces, is my company delivering the goods, you know? So something like that. I'm going to display the average quality of a vector of pieces there, which is something general, you know? It's not something that's specifically tied to being a good or a bad piece. But it's nothing difficult, you know? I'm taking my pieces, but I'm only interested in the quality of the pieces, not the rest. So I'm making a vector of qualities there. I'm doing this transform to just keep the qualities of the pieces there because I don't care about the rest. And then I'm calling an average function that I wrote on those floats to get the average value of my floats. Now, there's no average function in the standard library because it's much trickier than people think to write properly in a general way. It's a tricky one to do. It's fun to do in a class, though. So we need one. No? I'm sure everyone can write an average that returns doubles, but if you want something in general that works fine for your types, it's trickier a bit. This one is fine. No? It's making the sum of the values over the number of values, and we're hoping there's at least one value because I didn't guard against it in this case. So if you're passing it something that has 0 values, let's say you're in violation of my preconditions and I would need a contract to tell you to go to hell. Is that okay? There's going to be a talk on contracts by Timur in 2 days. It's a tricky topic. It's going to be fun. Questions about this? Cool. Cool. I'm letting the caller control the return type. Sometimes it's useful to have. And at the end, well, I'm going to wonder about the average quality of the rejects. Were they that bad? I kept them somewhere so I can compute things. So again, well, I'm going to take the rejects. But rejects, I have elements there where I have pairs that have like the name of the reject and the number of the quality or something like that. Yeah, the quality of it. So quality and I don't remember what the thing is. So I'm transforming my rejects into their qualities and then calling the same function to get the average quality that I got. Why not reuse the code I wrote? All of these things involve creating intermediate containers, which involves allocation and copies. That's annoying, but we've been doing that like that for years. That seems natural to us, but we're paying for something there. Okay. And then I have to do some in-depth analysis. But as I said, let's call them customers, the people who asked me to do this, well, they're doing that concurrently. So they have their own system. Of course, they don't have access to their source code, and I don't want to see it because I don't want to end up with an NDA or something. So I wrote my own. So I have this other thing. It doesn't need to be singleton, but they have one. So let's do like you do, you know? And analyze the valid pieces to see, well, what did it look like? How many do I have that many pieces in them? How many elements? What's the quality of them? Whatever. So I'm going to measure the time it takes, though, because that's useful to do too, because they do some important part of their work is there. So they want to know how much time it's going to take. That's more complex. So I'm going to have a thread pool. I'm going to launch worker threads in there. I'm going to dispatch the work to the worker threads. I'm going to give them a rendezvous point. Then I'm going to get the data out. But it's not that difficult, just more complex. So this one is simplistic, but it works. So I have workers, of course, just threads. And I decided to model my work with functions. Why not? Function does the job for that. Some people say, I don't like function, it allocates sometimes. Okay, but in this case, I don't worry about it. And I have a mutex to add stuff to the work queue and get it out. It's not the same mutex as I do for other stuff, so cool. So far, so good, I'm guessing. And I have a way to tell my worker threads to stop at some point, because at some point the program is going to complete. I'm going to stop stuff. So I have this condition variable guarded by mutex also, and some variable I'm going to set at some point to say, okay, that's enough. At that point, it's going to stop. But it's not going to stop right away because it's threads. You have to give them a chance to stop and tell them, okay, now it's time to stop. And they have to check regularly for that stop signal, and then they have to stop graciously because you don't know what they're doing at the time you're asking them to stop. Cool? But initially, I'm not stopping, which explains the files there. And when I'm getting work from the queue, well, of course, I'm doing it in a synchronized way. If there's nothing to do, there's nothing to do. Otherwise, I'm taking something, I'm removing it from the queue with the mutex on hand. I use optionals there. I like optionals. They do a good job at modeling this kind of stuff. So you got nothing, you have an empty optional. You got something, perfect, it's yours, take it. No memory management, simple, efficient. Cool? Cool. And then when I'm creating my workers there, well, I'm being told at construction time how many I need to have, so I'm just adding them to my vector of threads there. And each of them, well, until the work to do is done, until there's nothing left to do. Nothing left to do doesn't mean the queue is empty. It means someone told me, okay, that's enough. What do? Well, if I can get work, I get work and I process it. Then I go back to my loop. And if there's no work to do, well, there might be work to do later on. So I'm putting myself in a wait state, hoping for something to happen at some point. Now, of course, when I reach the end of my program, someone needs to unblock me from that state. It's very important. So when I unlock, there might be work, there might not be work. It depends on what happened. But if there's work, it's mine and I take it. When you get up from a condition variable, you have the mutex in your hands, so you're okay. Cool? Cool. And then, yeah, when I'm adding work, I'm making sure that I'm adding work in a synchronized way, and then notifying someone that, hey, if you're waiting, there's work for you. They're happy, so they jump on it. And of course, when I reach the end, well, I say, okay, that's enough. And I'm telling everyone, wake up. And I'm doing this, like turning my thumbs until they've all done the work that they had to do. At some point, the work completes. Something like that. So when I'm doing my analysis, I end up with results. Now, results could be complicated, so I went to the type. Nothing that complicated, to be honest, though. There's a number of elements there. And there's a map that says for that kind of reason, well, you've got that kind of, that number of elements and that quality or something like that. I don't really remember the details, but something really simple, to be honest. So to do the computation, what do I need to do? I need to split the work into pieces that the worker threads can handle, which in my case kind of looks like this. So my code, I decided to use 10 chunks. That's totally arbitrary in this case. It could be something else. I didn't measure the best load I should use. And I split my things into smaller n-sized bits. I have this integer that counts the number of tasks that have been completed, so up to big N in this case, because the threads will complete in orders I don't know of beforehand. If I want to know if they've all done their job, I need to know when the value reaches that point. And yeah, that's it. Yeah, that's it. So I need to free my thread pool there. So I'm adding, this is something I like, I don't know about you. I've been asked quite a few, oh no, not again. I swear this wire hates me. Is it back? AT, I hate this wire. I'm gonna kill it. I'm gonna get it back. I hate it. But I don't hate you, you're nice. I said, no, it's this one that's moving because I'm hitting it when I'm walking around. Sorry for the noise and the troubles. My screen is flashing, but we're gonna get there. At least you can see Pauline, so it's not that bad. Pauline is a nice dog. Thank you so much. Thank you so much. This is where I was? Yeah, this is where I was, pretty much. Thank you for being there. So there, as I said. This trick, I often get asked, when you have a for loop, can you use two variables of two different types to iterate stuff? Well, you can use two integers, it's easy. But if you want to use variables of different types, you can use that structured binding thing with INP there, use a pair or tuple, decompose it, and have fun. So I have two counting variables there, an integer and an iterator, and I'm using them both to go through my loop. I'm adding work that takes chunks of approximately the same size each, small n, and each of the threads works on that part of the vector. It's read-only, so there's no concurrent access, really. No, well, there's no worrisome concurrent access, just read stuff. And the lambda is mutable because it's going to update a few of the outside state in this case, which is not something you recommend, but sometimes that's what you need to do. There. So I need to perform the actual computations I'm asked to do, which looks like this. So this is part of the loop, it's a big loop. So I have the number of elements I'm checking, and I'm going through the set I've been given, B to E in each of the lambdas. And then I'm decomposing that B thing. I'm taking the value of star B there to take the element, decomposing it into two things, the integer and the actual quality. And I'm doing some computation and summing up the qualities and counting the elements. So it's like boilerplate code. It's iterating through a subsequence of data, keeping temporary data along the way. There we go. Then I need the average quality for each type of element, which is not that big again. Look at the fact, though, that I took a reference in my reference binding because I'm updating the state on hand. It's not external state, it's state that's within the container in this case. I don't even remember why, to be honest. And then I have to say I'm done, which is the important thing. So I arrive at the end and say, okay, I have my results. One done, plus plus completed. So at some point completed, we'll reach the big N mark. I'm going to be okay. And towards the end, I'm going to wait for the end. So at the end, I have this loop up there. I put blah there. I'm sure that other people are thinking blah right now. In French, it's buff. I changed it to bleh because I knew it was an international community there. So this is busy waiting. So we know it's not spectacularly good looking, but it works. So it was there. I'm hoping for a better solution one day, maybe later on today. So I'm waiting for everything to be done. And then I'm making some kind of accumulation of all the results with that weird merge that I put there that I wrote myself. I won't show it to you, but it's something that merges the maps. It's trivial stuff. So once I'm done, well, there's actually working bit of code there that's, I'd say, efficient given what I'm asking it to do. It's naive, but it works. When I mean it works, it actually produces data. Give me a second. Files like, ooh, you would not see this if I don't put it on the right screen, but now you will. So it's a huge, don't do that to me. It's a huge file like that that's about 1 gigabyte wide. The wires hate me. So I'm hoping this will stop someday. There we go. So, and when I say it works, well, you get numbers. So if you look at this, it took me about 5 seconds to create the stuff, but there's some randomness involved, and rolling the dice takes time. The sequential stuff took me 40 seconds. When I ran it, it's all optimized code, of course, as you guess. It's not debug mode. And then the deeper stuff that I'm doing concurrently took about half a second. So that's okay. So the entire process with C++17 code took me 46 seconds in this case. Which is a lot less than what they do. They have much more data and much more serious stuff to do than I do. But it gives you an approximate idea of the scope of the work that has been done on my machine. It's a recent machine, so it's not nothing. It's not a serious benchmark, but for the picture, it's okay. Cool so far? Working code. Took me a few hours to do. So then you say, okay, so I have something to do and I have technical debt. So I'm hoping that moving to this newer version of the language, now C++20 in this case, but it's going to be 23, 26, whatever. Maybe for you it's 17, which I hope you will like because it's a cool language too. Whenever you're changing tool, well, tools bring ideas, they bring ways of thinking about stuff. So you can rethink the way you do things. So sometimes the code will be slightly adjusted. It's not just a matter of changing words. Sometimes you have to rethink a few things. I'm not going to change the whole code. I'm going to sneak a peek at some bits and pieces where it seemed to be interesting to make changes. And I will do it in a before-after way so that we can see the before and after parts, not to revisit the whole thing. I just wanted to make sure that you had code that works. All the code is in the same drive as the slides are. Okay. So that absolute value thing there, which works. The code works. Add something like that, which is kind of cool. You can make it nicer, of course. That's kind of cool. It's a generic kind of thing. You can be done at compile time if you want it. Pretty efficient. If Const-Expr is still a good tool today. When you have decision trees to do, you have more than one algorithm, and there's a sequence of steps that you need to go through to pick the right one, it's a good tool for that. Now there's only one step. So for something like that, it's a weird hammer to wield, let's put it that way, to solve this kind of problem. With concepts, it could be nicer, but this thing could go much farther than what I'm doing right now, but concepts will come back again and again. But just writing it this way is already nicer in a bit, because you're saying, well, for unsigned integrals, nothing to do. And for the signed integrals and floating points, that basic algorithm there is okay. It doesn't change anything to the speed of my code. It might carry the intent a bit better. Let's see. I didn't have to check that my t was actually a number. So it's going to, someone is playing with my wires, but it's not my fault. So while I'm speaking, the other version it didn't show, but I could have passed a string there and gotten some weird error messages. Now with this one, I will get a message saying that my concepts are not being satisfied because I'm passing something as neither an unsigned integral, a signed integral, nor a floating point number. Tell me when I should close and restart.
You're all good.
Don't be sorry. I'm glad you're doing this for me, and I'm not doing it. So we should begin. This has been an experience this morning.
Yeah, I'm so sorry.
No, I still like you. It's not your fault. So we should be getting back our display in a second. It's telling me go back to where you were. And I should be able to go back there. And there we are. So I'm expecting better error messages at the very least if I'm using this with something that is insane, which we sometimes do because we're distracted. Now, this can go much further, as I said. Last year at CppNorth, I went quite far with this thing. I'm not doing that this year. The generic code looks normal. Let's go back. There's no template. There's no angle bracket. Sometimes you still need them. But it looks reasonable and covers a host of cases because it's conceptual. Love it. So these let you write code that looks normal. It's really cool. And you get better messages, which has been a complaint for a long time with C++ users, as we all know. This is, I'm guessing, this is probably one of the at least two biggest changes to the way we program that comes with C++ Swing. The other one being probably this. Lots of you, many of you have heard about that. There's talks about ranges. This is not going to be a talk about ranges, but we'll see the impact in practice. You know? So iterating over pairs of iterators works. It's flexible, it's efficient, it's been proven. And I would claim to say, I would claim some people will say, but I would claim that the standard library is a good example of solid engineering. It's well done. There are problems with it, but given the scope of that thing, it's a very high quality piece of software. And the people who maintain it are very good. So it's tiny flexible to use iterator pairs to do work. I took this example that I sometimes use with people who say, well, do I really need that? If you look at this one closely, it's expunging rejects from a vector of pointers to pieces. It could be complicated. It could be inefficient. But what do? I partition. So I put the good ones up front and the bad ones at the back. I'm getting pause there, which tells me where the first bad one is. Then I delete the bad ones and I keep the good ones. It's just raw pointers. It's very safe, very efficient. It's 3 lines of code. I could do something like that with remove if also. Cool. Nothing complicated. So we know, though, that we don't always use that flexibility in our code, and the common case is to go through the entire thing. When ranges came about, quite a few years back now, Eric Niebler had published a blog post saying that we could be more efficient in some cases and showing why. And when he worked on that thing, he put that forward. So taking that average function that I had, where I'm iterating over B and E, B included, E excluded, and making the sum of the values on the number of values, still not checking if it's 0. Most cases, I'm guessing people will be passing the entire container there anyway, begin and end of something. So in this case, using the range concept, so saying I'm accepting RG, that is anything that behaves like a range, and I'm accumulating over that because where there was no accumulate function in ranges when I wrote this, there's a reduce function now that does the trick, but I didn't have it when I wrote this. And I'm going over the range with the values and writing my homemade accumulate, very simple stuff in this case, could be made better, I'm sure. But this is something people would call with a range instead of with a pair of iterators and would essentially do the same job. I'm doing plus by default, but you could pass it something else if you feel like it. And then the average that I used to have with a pair of iterators can be tightened a bit by saying, well, IT is not just any kind of type. It has to be something that behaves like an iterator that lets you go forward. That's the thing I'm asking of it. So I could be hoping for better error messages when I'm making mistakes. And I could also have an average on a range, which lets me pass the whole thing, which is my default case. The other one's still useful, but I expect this one to be called more. So I'm computing the size of the range and then making the sum over the number of elements. I'm doing that n first because I'm doing forward of my range in there, which could be removed sometimes, so you have to be careful. Is that okay? Cool. So the code that I had, which used a vector of pieces, allocated, then kept the qualities, and then did the average of the qualities, which involved getting another vector in there and reserving space and getting the qualities in there and doing an average net. The whole thing looks like this now. This is kind of neat, though, because I am doing that average on something that's not even a container. I'm taking the rejects, but I only need the keys. So that's my first transform. But I'm not doing a transform really at this point because it's lazy computing. Once I have my keys and only my keys, then I'm transforming that to get just the quality. We have this transform thing that lets you get a single bit of your object. There's still no transformation to be done. There's still no allocation, no container involved. And that average is based on the initial value of 0. So this entire thing saves me 2 containers, 2 allocations, and a bunch of copies. The only moment where I'll actually do something at the end is when I go through the values and observe them. And only at that point will they be transformed. This saves us, as we will see later, quite a significant amount of time. Then I want to compare my pieces. Remember, I had all of those relational operators to write. I had 6. That could be much worse. But it's cool. We can write them. It's highly configurable. You could decide to make your less than and greater than operators behave in weird ways, but you won't do that because we will all hate you with a passion. So the whole thing before looked like this. It's a tiny slide with tiny fonts because there's a lot of code, but I have equal, equal, and then different from written in terms of equal, equal, and then less than, and the other 3 written in terms of less than because I'm not crazy enough to rewrite that thing and debug everything. So if we move to C++20 step by step, the first thing we can notice is that boilerplate-ish different from that we always write, it's always written the same way unless you're really looking for trouble. So you can just get rid of it because the compiler will do it for you. If you had written a sine operator equal, equal, you don't have to write different from anymore. It's given. It's free. Because we know how to write it. And past that, well, all of those things that I wrote in terms of less than, they will not be synthesized for me automatically, but what I can do is write what we now call spaceship, which is a 3-way comparison that gives me something that tells me whether A comes before B, is equivalent to B, or comes after B. So with this one well written, if I want it, I can end up with 1 operator to give me the other 6. And they will be synthesized and I can use them in my code. They actually kind of exist when I call them. Now, I didn't even write the code because I was doing simple lexicographical comparison of my members in order. So I'm creating tuples. and using their spaceship to do the work. This was trivial to write. It's actually very efficient. So if, because sometimes it happens, you are fine with this kind of implementation, well, writing the relational operators has become almost trivial. When it's not trivial, you need more care, but there are rules for that. And this is not a talk about spaceship. It could be cool, but you have to look at the rules. If you're looking at types that don't behave that way, go look deeper. Sometimes, as people have noticed, we can write equal equal more efficiently than we would write our spaceship operator. Vector is a case that was found. I think it was by Barry Revson. He said, well, I can write my equal equal more efficiently than if I write spaceship for vector, because I will first take into account the sizes and not care about the rest if they're not the same size, which is not something that you will write with less than. So in that case, well, you write equal equal, you write spaceship. Equal equal is used for different from, and spaceship is used for the rest. So you write 2, which is much better than 6. Cool so far? Awesome. Then when you're changing your code, one thing you want to think about is the interface of your functions, because they're telling you stuff. You know, the names tell you stuff, the arguments tell you stuff, the return types give you stuff, give you information. So you want these things to convey the right message to your users. And you also, I think, want your interfaces to accept the minimal thing that does the job for you, such that they work for a wider array of types. As long as it's doing the right thing, it's not dangerous and it's efficient. So things like this at the lower end. I was requiring a vector of element types when constructing my piece there. But I don't really need a vector, to be honest. It could essentially be any container, but I expect, in the kind of code that they write, they expect things that are contiguous in memory. That's reasonable for their use cases. They won't be using linked lists for that. So requiring a vector there is overkill. I mean, someone could want to pass an array there. Why stop them? Why stop them? there's no good reason for that. So now we have span. But there's the important change. Look back. I used to have a const vector ref. The vector was passed by reference to avoid a copy. It was const to avoid us mutating the elements in there. And now I have a span passed by value of a const type, because the span behaves like a reference to the original object. So if you want constness, you have to put constness on the type of the element. It changes strictly nothing to the code that calls me. Just opens up new opportunities for calls with other types that do no harm. It's just a good interface, the better interface than the previous one. Yeah. So we're requiring contiguous in-memory elements, and we're saying we won't damage them because we mark them as const, but that's pretty much it. There. There are other cases in there. So that evaluate quality there. I was passing a vector and then only using vectors, but if you look at the code there, there's nothing preventing me from using it with an array. Nothing would change, especially if I use the begin and end free functions. I can move to span. Cost me nothing again. There's no cost to that. There, same thing. There's a number of places in your code where you're requiring more than you really need. I'm pretty sure. This is interesting though. So I have my average quality with a span of pieces, and I have my vector reserving values, getting the qualities, doing the average. And I can make it even simpler there because I can use the transform from ranges where I'm making a view. Qualities there is not a container. It's a view over the original data where I get only the qualities and then I'm averaging them. I could even get rid of the qualities variable there and just merge them out to the call to average. It's going to be okay. I think it's code that talks well to us. It's no less efficient. In fact, it's more efficient than it used to be. It accepts a wider array of types. It communicates intent well. I like it. And it's less typing. It's less typing. I love less typing. There. So there's no actual container to be done there apart from the, well, no, there's none at all. It's just a reduction. So span is cool. The span is a pair begin size essentially. It's lightweight. It's kind of like string view, but it doesn't let you change anything. String view doesn't let you change anything. Span lets you change stuff. So you have to mark your elements as const if you don't want them to. And it's a safer interface than array, so why not? Okay. So let me accelerate a bit because time is flying. There's that text formatting thing that people keep complaining about. How many times have I heard real programmers use printf? I want my display on the console to be fast. Yeah, right, why? So, wires. So I have this format integral thing that I had with my static assert that says, this has to be an integral. And I call pad left lower. This is what I used to have. It worked. I insist it worked. I can make it differently. Instead of having a static assert, I can say, well, I'm accepting an integral. So I will fail if you're not calling it right, and I'm going to get a proper error message for that. And I can use format there instead of doing my acrobatics for pad left and stuff because it's all built in. It's pretty nice. It's a syntax that you have to learn, though. This says there's padding to the left, then the thing is aligned 3 digits to the right, and whatever, but it actually does the job. And it does the same display. It's not faster. It's not faster. It's equivalent in terms of speed, probably maybe a bit faster, but it often carries intent in a clearer manner than many lines of chaining calls to an output stream with different manipulators, and there's less to know. You know? There. So, yeah, efficient. If you don't like doing it this way, another way to do that is to write your own type. When I want to format an integer, I'm going to make a formattable integer out of it. This case, I'm keeping the integer in there. I'm asking it to be an integer, as you can see, because it's a concept. So it only applies to integrals. And I wrote that spaceship thing there to make sure I can compare my formattable integers together. And to be using format, though, I need to write some code, so we won't go into that. But as you can see, I have a formatter specialized for a formattable integer of t. And there are rules there. If you want to know more about that, Barry Revan had a talk at CppCon last year. It was a very good talk, specifically on that thing, but very dense in an hour. I won't go there. But if you want to know everything about ranges, not ranges, but format, go there, it's a good thing. But having written the proper boilerplate for your code to be displayed, you can do something like that. I'm going format and passing as argument, not an integer, but a formattable integer. It's going to format right. If I just pass an int, I'm going to get an int. So it's a highly configurable, personalizable tool that you have in your hands now. It conveys the intent well, doesn't it? I think it does. So yeah, you can replace things like that, where I used to have a const string ref, but that's annoying. We know we prefer string view these days, but with plus it didn't compile. Nasty. With this, it's got to format the right way. My interface is better. Didn't change much. I used to have something like that with a chaining of messages like this. And notice the way I display the milliseconds at the end. I have to do my duration cast and then do a count because there was no way to display such a thing as a millisecond on a string before. C++ really changes that. So we can just do that. It's going to give me the number of milliseconds followed by ms, which is unit, no space in between. That's a bit of an annoying thing, but it's a political issue. But I think it reads right. I have my formattable integer, my duration. There's no acrobatics to explain to anyone, why are you writing count there? Oh, I'm just outputting my number of milliseconds. It's going to display right. I think it's cool. And there's, still have a few minutes, there's this multi-threading thing that I had. Remember, I had this thread pool I had to write. We still have to write thread pools these days because there's no standard one. I know. But we had something like that with thread that I needed to join at the end because your threads, you have to either join them or detach them and let them fly away like butterflies, you know, which we do in async. And this done variable there said, okay, stop it. It's a manual solution to a well-known problem, a rendezvous point. There. I can do this now. So I can use joining thread. J has nothing to do with Java. Don't try. That's not how it works. And a stop store is there. So a stop source is a synchronization tool that lets me from one point say, okay, that's enough. And from the other points, consume that information, say, okay, I understand. It's cool. It's time to stop now. since I'm having many J threads there, I'm using a single stop source. It's easier for me. And when I'm doing my code, I used to do while it's not done. Now what I'm doing is, well, I'm taking the source token, the token from my stop source, and I'm looking for a stop request. It's the same code, really, but it's standardized. It carries the intent in a way that everyone will understand. It's standardized. It does the right thing. Okay. Cool. And I used to do that. It's done. Everyone knows about it, and I'm flipping my fingers. Now I'm going through my source and saying, I request a stop. I inform everyone, and I'm waiting for the join there at my destruction point because all of my threads, being J threads, will join on exit. Of course, I have to make sure that they stop, or else I have a deadlock, but that was already the problem before, wasn't it? Cool. And there's this rendezvous thing. The number of completed things there that started at 0, and I counted in each of my threads that I had completed one more step, and at the end I had that busy waiting thing that was inefficient, but sometimes you only have so much time to write things. You have to be careful though. In there, when I'm putting my results in the container that contains the result, I have to lock a mutex to make sure that my introduction is synchronized, but that's a minor thing. And yeah, this is inefficient. And now I can use a latch. We have that thing. We have latches and barriers. Latches are used once and barriers are reusable. So this is a use once thing. I have a latch of n+1. You're going to say, why +1? You have n threads. Well, the one that starts them is going to participate in the rendezvous point too. So that's the +1 there. So when my threads arrive at the end, they say, arrive and wait, la, 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 which does the counting for me, in an efficient way, not a busy wait thing. And when my, the main thread in this case, that starts up the work, arrives and waits, it waits like the others. Now, when they all complete, this is the only one that has code after that. So it's going to continue and return the value. Very smooth, very efficient. You have to be careful, though. In this case, my locking and inserting of results is put in between braces inside. I wanted to point that out efficiently because if I'm doing arrive and wait with the mutex in my hands, I'm going to stop everyone from working. You have to know what you're doing, But it's still much better. It carries the intent in a much clearer way. It's something that we all do. There's patterns for that. So yeah. And at the end, I won't spend too much time on that, but these discrete pieces there that's doing a vector of pieces, which we did, we could do that with a generator and do code like this, creating pieces with co-yield and stuff. If you want to play with coroutines, there's a lot of code to write to get there, though, with code like this. The problem is that this is not a good use case for it. I'm going fast because it's 11:56, but the problem is I'm not doing really I/O, I'm just generating stuff, so there's overhead with the generator or the coroutine code, and I'm not getting anything in result. So as you will see, my code that uses that is slower. I wanted to point out to these people that if you use that, you have to use it for the right ways. So, yeah. The reason why there's so much boilerplate to write, if you're wondering, is because we standardized that very, very, very late in the process because there were 1, 2, no, 3 competing approaches to coroutines, and it took forever to decide on the right one. It was difficult. But still, there's so much more. So we could do so much more than that. I didn't talk about consteval, although it's very cool. Ben has done something on consteval a few years back. It's really, really cool. ConstExpert does so much more than it used to, and I almost didn't use it there. ConstInit solves some initialization problems. I didn't use it. It's cool. We have dates in Chrono that's incredibly useful and difficult and just right, it works. There's a talk on calendars this week. I think again it's Ben. We have ways to select at compile between compile time and runtime algorithms based on whether I'm ConstExpert or not. It's a gigantic standard. I barely scratched it. But you're wondering, okay, so is it worth the trouble? You worked for that. So I used to have these numbers. I have these. It might not shine now, but let me show you numbers in bigger font. So the first part is my old code to generate pieces was faster than my new code, but that's because I'm using coroutines where I shouldn't. That doesn't mean coroutines are slow. It means this is a bad use case. Okay? Cool. The ranges shine because the number of copying and allocating I didn't have to do in the new code to get the same results makes a significant difference in this case. So if you want throughput, this shows you that ranges good, well used, you're going to get throughput from that. And coroutines would be faster too if I had used them in the right places. And the thread pool is not really faster. Sometimes I get faster results, sometimes slower, depending on what I'm doing. The point is it's clearer. It does a better job at expressing intent. I don't have to rewrite the world. The latches do what they're supposed to do. JThreads do what they're supposed to do. Stop tokens do what they're supposed to do. You understand better the code, you don't have to reinvent the wheel. So the overall, well, gave me quite an upgrade, to be honest. Okay? But the whole point of that, even 59, I'm almost done, isn't even the speed. It's the clarity of intent. You're writing code to be read sometimes, I think Kate said. It has to be fast too. So you can raise the level of abstraction. I use ranges. I use concepts. I use spaceship. I use format. I use latch. The message, and there's so many others. The message passes better, clearer, I think. So, should you be using that? Tell me what you think.